All right, so let's get started. So today we are going to, so in the last class, we mainly focused on the properties of the perfect crystal, okay, so without any defect. So we obtained the lattice parameters and also the bulk modulus, which is the inherent or intrinsic properties of the crystalline state. Okay, so today we are going to talk about the defect. Okay, so and first we'll talk about the point defects, and second, among the various kind of the extended defect, we are going to discuss about the surface specifically. All right, so the first, the point defect. So you may know that in a solid there are two types of the defect. Okay, the first one is point defect, which is consists of a few atoms, right? And extended defects, which is spatially extended, like, and then there are many atoms are involved in forming those extended defects, like dislocation or the grain boundary or twin boundary. All right, so first the point defect. The point defect here, this figure shows the well-known point defect, and the material, the base material is some kind of the ionic compound. Okay, so the red one is anion and the blue one is a cation. So like magnesium oxide or sodium chloride, this is the schematic picture of the binary ionic material. Okay, so the most well-known might be the vacancy, because sometimes the anion site is vacant or the cation site is vacant. Okay, so those atoms are such a defect that has the empty sites are called the vacancy. And there are interstitials. So interstitials mean those atoms are placed inside the material, and when the anion atom is inserted in the crystalline site, then it is called anion interstitial, or cation interstitial in this case. Where is the, okay, so this is the cation interstitial, all right? And or sometimes external atoms called the dopant, okay? We are intentionally or unintentionally, external atoms are get into the material, and if it is take up this interstitial site, then it's called the interstitial dopant, all right? And but when those external atoms are replacing one of the atoms in the host material, like anion or cation, it is called substitutional dopant. All right, the both are possible. And for simplicity, this the vacancy of the X atom is called, has this the short name, that's Vx, or when it is interstitial, then it is called Xi, all right? So for instance, if it is oxygen, then VO means oxygen vacancy, all right, for instance. And sometimes the two atoms, anion and cation, are actually misplaced, okay? So for instance, in this case, it is called anti-site. Here, this defect means that originally it should be taken up by the cation, but here it is anion, so it is anti-site of the anion replacing cation. Okay, so this is anti-site, and there are defect pairs, like in this Frankel pair, it is the pair of the vacancy and interstitial atoms. All right, with the same type of the vacancy and interstitial. Or the Schottky pair, it means the vacancy of the two types, or both anion and cation. So if the vacancy is formed in pair, then it's called the Schottky pair. All right. So in material, there are numerous kinds of the point defects are possible. All right. Of course, among them, maybe the most important thing would be input defect would be the interstitial and the vacancy defect. All right. So the point defect, even though it is a defect, actually it always present even in the perfect solid. Okay, so suppose that you have an ideal, some synthesis method and a synthesis experimental setup, and you have grown up even with every atom in the right place, a single crystal, right? But even in that perfect solid, we always have the point defect because it is favorable thermodynamically to have a certain density of the point defects. I will show that by using this the free energy of the model system. Let me. All right. So, okay. All right. Okay. All right. So maybe you have seen this kind of derivation in the thermodynamics. Suppose that in a solid, it consists of the n atomic site. Okay, so n should be a macroscopic number like Avogadro number. And suppose that the vacancy formation energy. The vacancy formation, we will talk about this quantity frequently in this today. This is the energy. Then you need to create one vacancy by displacing one atoms in the perfect site. Moving into another crystalline site. It's a little bit complex, difficult to imagine, but you know, making the vacancy, and this atom should be go to the another crystalline site. Okay, so that is called the vacancy formation energy. This is the energy that you needed to create one vacancy. All right. So suppose that that energy is EV, the vacancy formation energy. Then the Helmholtz free energy. So in a solid, if we neglect those pressure or the volume, the variation, then we should minimize those Helmholtz free energy, which is consists of the U and T times entropy, U minus Ts. All right. So the Helmholtz free energy in this case to create the low vacancies from the n atomic site in the unit volume. So okay, so this n is the atomic site in the unit volume, and the low is the number of the vacancy you want to create in the unit volume. All right. So this free energy, so U minus Ts, and the energy. Since you have created low vacancies, so you have to provide rho times EV energy, right? So it is higher by this this magnitude of the internal energy to make the low the vacancies in the perfect solid. All right. Okay. So the U is increases by rho times EV. All right. EV. And about entropy, the entropy here is the correspond to entropies, you know, K log W. W is the number of the possibility. All right. So you have this n possible site to make the vacancy, and the total number of the possibility is the combination of the choosing the low site from the n site. Okay, so it's combinatorial of the n and the low. Okay, and here the K is Boltzmann constant, and T is the temperature. All right, and in terms of the factorial, you can present in this here, so m factorial over rho factorial and m minus rho factorial. And using the Stirling's formula approximation, you can expand this factorial with in this form. Okay, all right. Okay, here like that. And now, since the free energy or equilibrium state means that the minimum of the free energy, so the derivative of the A with respect to rho should be 0 at the equilibrium condition. All right. So the partial derivative of A with respect to rho is EV minus KT of this formula, and here it is simplified like that. And also, since the vacant site is far smaller than the atomic site, and so we can approximate this m minus as n. Okay, it's a little bit tricky to moving the. Okay, so m minus with the n. Okay, and since this should be 0 at equilibrium condition, so this means that rho divided by n is which corresponds to the density actually, or the probability of each site is taken up by the vacancy is nothing but exponential of the minus EV over KT, so which is the Boltzmann factor of the vacancy formation energy. All right. So this is the equilibrium concentration of vacancy. What you can see is that even though this EV is a finite positive number, at any temperature, finite temperature, unless it is absolute zero temperature, you always have the finite equilibrium concentration of the vacancy. All right. So suppose that T is 0, then this is the minus infinity, so this is 0. So there's no vacancy. But at any finite temperature, you always have a certain density of the vacancy at the equilibrium condition. All right. So in this respect, this the point defect is called the thermodynamic defect or equilibrium defect because it is the defect that exists at the equilibrium condition or okay, even for the perfect solid. All right. Okay, so all this the vacancy, this term comes from actually from the entropy contribution of the vacancy, right? By making the vacancy, we have the more number of the possibility of in the configuration space. All right, that's the key point to for the point defect. All right, so it is point defects are unavoidable. Okay, it always exists in your material, even though you make it perfect. Okay, so but in many cases, we when it grows the material, it is grow in non-equilibrium condition. That means we have the far more defect than is supposed that is assumed that is predicted by the equilibrium concentration. So most of the material has the quite large number of the defect, and it influences the material's property actually, even though it exists at a small amount. For instance, in the mechanical property, mechanical properties, if you add up, it is known that if you add up a small concentration of the external dopant, then it changes the mechanical property quite a lot. And it is known that those external dopants actually affect the motion of the dislocation, which is critical for the mechanical properties. And also the vacancies intersection, we have seen in the 2 weeks ago that the diffusion property of the diffusion property is affected by the vacancy. So vacancies mediates or interstitial mediates the diffusion of the atoms, right? So the concentration, finite concentration of the vacancy and the interstitial is strongly related to the diffusion property of the material. And also about the optical and the electrical property, right? So some of the defect affect absorption of the emission spectrum, which means that you have different color of the material. In this example here, this is a synthetic zinc oxide crystal. So without any defect, zinc oxide is a band gap of 3.4 electron volt, which is transparent, right? But if you have a certain concentration of the oxygen vacancies, then depending on the concentrations, you have the red or the green colors appear in the material. So usually some of the defects are called the color center because it changes the color of the material. All right. And also in the case of the TiO2, since the TiO2 has the band gap that is larger than usual the visible spectrum, so by inducing the defect inside the band gap, you can increase the absorption of the TiO2, solar energy absorption of the TiO2, which can increase the performance of the solar cell applications. All right, so sometimes it's quite useful. And electrical properties, the non-stoichiometric defect in many of the ionic materials actually is known to increase electronic conductivity, like a TiO2, right? This is, TiO2, zinc oxide, and zinc oxide, they are the, well-known insulator if you make the perfect stoichiometry, right? However, since there are non-stoichiometric defect, which means that you have the slightly less oxygen or slightly more oxygen, in that case, you have the electronic conductivity that is comparable to many semiconductors. All right, and also in the case of yttrium-stabilized zirconia, you can increase the ionic conductivity or electronic conductivity or ionic conductivity by inducing the oxygen vacancy. which is used in the fuel cell applications. And in the case of the external electron conductivity of the silicon, you know that there's p-type doping or n-type doping, right? By providing the external dopant, you can change the electrical property quite a lot. This is the bad thing, that defect levels in the band gap sometimes play as the recombination center of the electron hole. So the solar energy is absorbed and the electron hole pair is created, but they can recombine at the defect site, which can kill the source of the energy. All right, so it's really important in many properties of the material. So it is really important types of the defect. Besides the point defect, we also have the extended defect, which consists of the many extended atoms extended over the space. Like you may know that this is this picture I got from the Callister's the textbook. There's a screw dislocation or the edge dislocation, or in the polycrystalline samples, you have the grain boundary between the different crystalline grains. All right. So those defects are actually extended over the space, and so therefore, it actually energetically it is really expensive to create this kind of the defects compared to the point defect. And also, because of its a larger size, there is no entropic contribution, the real significant entropic contribution. So they are not thermodynamic defect, which means that by using some appropriate experimental procedure, you can actually eliminate those defects, right? Like the thermal annealing or high temperature growth. All right, so here we focus on point defects. Then how can we model this the point defect? So what here we want to address is that we imagine that perfect solid, we have one type of the point defect, and we want to focus on the property of this isolated point defect. All right. But in order to model this such a system, you may need infinite size of the atoms, right? Because it should be a much more macroscopic material, which is computationally is not feasible. All right. So what we here, our strategy to make this feasible in our computation is to actually repeat those defects in a periodic way. Like for instance, if you want to describe the vacancy, instead of the one vacancy and infinite solid, you actually repeatedly make a kind of the a super cell with one vacancy is repeating in each cell, right? Which is the far bigger than the original unit cell. And if this superset is sufficiently large, then you can assume that it corresponds to the isolated defect. All right. So this is the that means that we are going to impose the periodic boundary condition in our modeling, right? So why we stick to this periodic boundary condition? Because it is the comparable with most of the codes are actually work with the 3D the periodic boundary condition. So such an supercell approach actually comparable with most of the existing code. And also mathematically it is much more convenient, for instance, to evaluate electrostatic energy, and there are many also mainly because of the Fourier transform. Such a periodic boundary condition is always mathematically much more simple than the other boundary condition. And also in the case of the quantum modeling, actually this periodic boundary condition is compatible with the basis set, because we are there, we are going to use the mostly the Fourier analysis. All right, because of this, the reasons we always want to model those defects within the periodic boundary condition. Okay, so specifically in this case, for instance, we are repeating this vacancy in the 5 times 5 of the unit cell. So this green one corresponds to the unit cell, and we are repeating in this vacancy 5 times 5 periodicity. All right, so suppose that this is big enough, the interaction between the two vacancy is very small, then the property that we extract from this this supercell would be correspond to the one single isolated defect. All right, you understand that? Then how we know that this 5 times 5 is big enough? Okay, so but there is no well-known rule to set this defect, but usually this chemically that if the two defects are apart by, let's say, 10 angstrom, then usually there's no chemical interaction between them. So that's always the safe number, okay, to get the repetition by about 1 nanometer. Okay, that is a rule of thumb that works in many cases. But for the more serious test, you have to increase the supercell size one by one and check its convergence of the certain property. For instance, if you are interested in the defect formation energy, then you calculate defect formation energy at different supercell length, and you check this convergence, and you can say that, well, okay, so 5 times 5 is big enough, or it is not big enough. You have to increase up to 7 times 7. Okay, so for more serious tests, you have to systematically increase the supercell lengths. All right, so okay. And one thing that we have to keep in mind is that defect, if you introduce certain types of the defect, whether it is point defect or extended defect, it usually causes the atoms around those defects is displaced away from the original crystalline site. Okay, or that is to say, it makes a certain kind of strain field around those defect site. For instance, if you put one atom at the interstitial site here, then you can expect that those atoms around will be repelled from original site, right? Because of the finite site is pushing those atoms to the outside. Okay, and that will cause some of the tensile stress around those defects, right? These atoms are displaced outward, the tensile stress. Or if you put the smaller atoms like where is it? It is not here, but okay. So for instance, if you substitute one of the atoms with the smaller atoms, then it can pull those surrounding atoms, which may result in the compressive stress. Or so okay. So in order to due to this complex strain field, it is necessary to relax the atoms for any kind of the defect study. All right, and also the supercell should be big enough to accommodate those strain field. Okay, and compared to the vacancy, interstitial defect usually require larger supercells because it makes a larger strain field, as you can expect from this. Okay. Expect from this figure. All right? Okay. Everything's okay? All right. So how can we make the vacancy? So you will practice this in more detail in the next class. But you simply just remove one of the atoms from your supercell. You repeat it, and then you remove one atoms, okay? And then you relax the atoms using one of the relaxation methods that we have learned in the last class, and you can see that this potential energy decreases, right? Which means that the atoms are actually relaxed to minimize those potential energy. And for instance, if you remove the carbon atoms in the silicon carbide, then neighboring silver atoms relax outward, okay, away from those original site by maybe less than 0.1 angstrom. In the case of the 222, and the case of the 333, it is almost the same, 0.077 angstrom. So from this relaxation pattern, you can say that, well, maybe the 222 is big enough. Just by repeating, 2 times along each direction might be enough to accommodate those strain field. All right? Okay. So what we can learn from this defect calculation is the vacancy formation energy. This is the energy to create one vacancy. So the mathematical definition is that, the thermodynamic definition of this defect formation energy is the, since you have removed one of the vacancy, so the vacancy formation energy is the difference from one system to the other, right? And the other. And the one system is the vacancy, and the atoms that is displaced from the vacant site is somewhere in a thermodynamic or the chemical reservoir, right? Which is represented by this chemical potential mu, all right? So that is to say, so in your system, you remove the displaced one of the atoms and you take it out to some of their chemical reservoir. All right? And it is represented by the chemical potential mu. All right? So for the same type of even for the same type of the element, this chemical potential can vary depending on the situation you have in your system. All right, we will see that, which we will discuss right after here. So, for instance, if we are making the carbon vacancy in a silicon carbide, if your system, if you are assuming that this removed carbon atoms goes out as an atom, that is to say, if you are removing one of the carbon atoms and you are assuming that this carbon goes to the atomic site somewhere, then this chemical potential mu is the energy of this atomic configuration, which is the 0 in our definition. Therefore, the mu should be 0. All right. But if you are assuming that the carbon atom goes into some part of the diamond, okay, which might be the condition that if you have this silicon carbide is in equilibrium with the diamond structure, in some, where you have if you have enough the carbon atoms, and somehow you made the silicon carbide may grow or get in touch with this diamond, then the carbon atoms you are removing actually should be go into one of the sites in the diamond. All right. In this case, the mu should be equal to the energy, chemical, the Gibbs free energy of the diamond, or in our case, since we are talking about the 0 temperature, so in this case, this is simply this cohesive energy or formation enthalpy of the diamond, which is 7.37 electron volt. All right. So depending on your condition, the mu can vary a large amount of the difference, right? And in many cases, we control this chemical potential using the pressure of the gas phase. For instance, if we are dealing with, this one, the manganese oxide, then the oxygen chemical potential is actually controlled by the vapor pressure of the O2 gas that you have in your system, right? So you can reflect this experimental condition in deciding this chemical potential of a certain species. All right. Okay. So. All right. So here, given this the chemical potential, you can calculate this the vacancy formation energy using this the formula. All right. Okay. So specifically, in the case of the mu is equal to 0, or if it goes to the atomic site, then the formation energy is 11.43 electron volt, while in the case of diamond, since the diamond it is lower by 7.37 electron volt, then the vacancy formation is as low as 4 electron volt. All right. So which means that it is easier to make the vacancy if those atoms are in a more stable state. You understand that? All right. And you can check the convergence of the supercell by making a different size of supercell. In this case, the formation energy is exactly the same between 2 to 2 and 3 to 3, so which means that 2 to 2 is big enough. All right, and during this hands-on section, you will learn about the calculation, calculate the vacancy formation energy in the copper, right? And for the unary system, it is reasonable to assume that those vacant atoms goes to one of the another crystalline site. All right. So for the unary system, the chemical potential is actually determined by the crystalline state energy. Okay. All right, and this is the example, the input file, and you will follow this procedure. And from this, the vacancy formation, you can calculate this, the vacancy density, and at a certain temperature. So at the normal temperature, usually, since the formation is usually several electron volt, so at the room temperature, you expect almost a zero vacancy in your system. But when it goes to at the elevated temperature, like 1000 Kelvin, then this vacancy concentration, it becomes quite significant, right? 10 to the 17 per cubic centimeter. All right, and the second example is about the aluminum interstitial or substitutional defect in the copper. Okay, and you will also follow that. All right, so we have talked about the, and then we shift to this interstitial defect. Any question? Okay, let's continue. Then next we'll talk about the interstitial defect. All right, so interstitial defect is there are two types actually. The one is the external interstitial or impurity interstitial. You have the external atoms in your system, and if it is small enough, then usually this external dopant or the defect goes into the interstitial site of the original crystals. For instance, carbon in iron. Okay, that's the most famous example. Or sometimes the self-interstitial means the original atoms in the crystal can be, interstitial itself. It is called self-interstitial. The formation energy of the interstitial is calculated in a similar way, but in this case, you have the one extra atom in the interstitial. Therefore, you have to remove those energy or the chemical potential of those atoms from the interstitial, the energy of the supercell, including the interstitial. And in the case of the self-interstitial, which means that mu is the atoms, the interstitial atom is the same as the original host material. In this case, the mu is equal to the perfect energy of the perfect crystal. So it's simply n+1 times the bulk energy over the atoms in the crystal, or the energy of the atoms in the crystalline state. All right. And one tip is that since the interstitial causes a larger relaxation around the defect site, because it get into the space, and therefore it pushes out atoms quite significantly. So in many cases, we first start from some of the initial gas. So when in the case of the vacancy, you simply remove the atom. So that's the very good starting point, right? And the atoms relax afterward. In the case of interstitial, you have to put atoms at a certain specific position, right? And it requires your guess of the initial position. And in most cases, your guess is wrong, and you put the atoms in a quite crowded area, right? And it causes lots of the atomic force, or lots of the stress around to the atoms around the defect site, which means that the atoms initially, atoms around your initial starting point will have extremely large force, right? Extremely large atomic force, and therefore just carrying out the usual. So which means that your energy surface, among this energy surface, you are quite away from the equilibrium state. So just by simply using the well-known algorithm like the conjugate gradient or stiffness distance will not work that very efficiently. So in this case, the safe solution is to using the damped empty dynamics. So you are just moving those atoms, along the empty trajectory with some substantial damping term, and that it will, lower your energy quite safely, right? Okay. All right. This is an example of the self-interstitial in the silicon. It is very well-known problem in a semiconductor. So there are many possible types of the self-interstitial. So unlike in the silicon, the vacancy, there's only one type in most cases. But in the case of the self-interstitial, depending on how the atoms are placed, you have quite different types of the self-interstitial. Of course, there's only one interstitial that is most stable, but you have the local minimum for other types of the self-interstitial. That's the key point, all right? So for instance, maybe in the case of the silicon, the hexagonal is the most stable, maybe. For instance, let's say that this is 1-on-0 split, this is hexagonal and tetrahedral. So each type of the distinct types of the interstitial will have its own local minimum, but what is relevant is the most stable one. Okay? All right. So in the case of the 1-on-0 split, which means that this one of the interstitial atoms form like a dumbbell-like structure with original atoms in the original site, okay, like a dumbbell, or this is a hexagonal site, okay, and it is a tetrahedral site. All right. So in our case, we have to try, every type of the possible defect and compare the formation energy, and we decide which one is the most stable or lowest formation energy. All right. And in the case of the FCC, it is known that many of the FCC material, the metal atoms are 1-0-0 split, the split along the 1-on-0 direction. And in the case of BCC metals, there are many different types of the self-interstitial. And one of my contribution in this field is to is traditionally it was known that in the case of the vanadium and the molybdenum, the 1-on-0 split was maybe most favored, but from the quantum modeling I have found in many years ago, more than 10 years ago, I found that this is the crowd ion, which is a crowded configuration. This because this direction is the most crowded site, but somehow it is most stable, surprisingly, in the BCC metal. I guess that is one of my contributions in this field. All right, so you have to try various kinds of interstitial configurations. And in the practice session, you will try the defect, interstitial defect in the silicon. All right, and this is the other. Okay, so here by using of the damped MD, you can. So this is the initial structure, your initial gas, but which is quite different from the final equilibrium structure, right? So which means that your original structure will have large atomic forces in the atoms, and so therefore to make a stable minimization, you may try this damped dynamics. All right, this is hexagonal and this is tetrahedral. All right, and you can calculate this formation energy, and you can see that they are more or less quite similar, but among them tetrahedral interstitial is turned out to be most stable in this classical potential. Maybe the real answer, I'm not sure, maybe the hexagonal might be most stable actually in a quantum mechanical and experimentally maybe. All right, so that's the end of the point defect, and then we'll move on to the surface. Any question? Okay, so this surface is a kind of the extended defect, but it exists in any kind of the finite material, right? Even if you make a single crystal, it has a surface, right? If it's finite material. But the surface has its own importance. Like, it is usually many of the catalytic reaction occurs on the surface of the catalyst. And also the growth, when you grow the material, of course it starts from the surface. Okay, so knowing the surface is very, very important. And this is where the nanomaterials are very popular, and the nanomaterials have high ratios of surface to volume. So it is important. So this material, the property of this nanomaterial is dictated by the surface in many cases, especially for those really small nanoparticles. Okay, and you know, in a academically, this surface is very interesting because many of the various experimental techniques like scanning tunneling microscope or AFM or EES or protein vision, these are quite sensitive to the surface configuration. So you can see, actually using the STM, you can see each atoms, right? So it is really a good, good tool to know about the real materials. Okay, so surface has is really important. All right, so the basic thing is we have to index the surface if it has many different directions. And here I'll explain the so-called the Miller index. This is given like that. So suppose that this yellow, so this the unicell is in this violet the box, and suppose that your surface is consists of this yellow part. Okay, then you can find this intercept along each axis, like along the x-axis, it cuts at the half of the lattice parameter, and in the case of the y, it cuts at the b, and here in the case of z, since this is parallel to the z-axis, it is set at the infinite, right? So you have the three intercept, half of the a, and the b, and infinite. And the Miller index is actually the reciprocal of this number, okay? And it becomes the 210. So this is 210 surface, okay? We call it. In the case of the cubic lattice, there are very well-known high and low index surfaces, like this is a 0, 1, 0. And so this yellow are 0, 1, 0. And this one is actually by definition it corresponds to the 0, minus 1, 0, but by symmetry it is equal to 0, 1, 0. And this is 1, 0, 0, which is the surface cutting the x-axis, and this is 0, 0, 1, and this is 1, 1, 0, okay, etc. And this is 1 on 1 surface. Okay, so this is an example of the cubic lattice. Let's look at this atomic configuration of the surface. So this is a gold FCC crystal, and if you make a surface in the 100 surface or 001 surface, then you make a surface at along the G direction. Okay, and if you see from the top, it will look like that. Okay, and this is the 101 surface. If you look at from the top, then it will look like that. Okay, this is hexagonal lattice. Okay, all right. And this is the previous example was the unary system. And in the case of the compound, this is a little more complicated. In a high symmetry material like this MgO, 1 over surface look like that. Okay, so there's only one choice. But in the case of the strontium titanate, which is well-known perovskite material, even for the 1 over surface, we have the two different types depending on how you cut this material. Okay, if you cut at the top here, then your surface will be strontium oxygen terminated. All right, the top will be strontium and oxygen. But you can also make the surface such that this TiO2 is exposed at the top. All right, so this is TiO2 terminated surface. So for many materials, actually, this index is not enough, and even for one type of the index, you have different terminations. And which one is more favorable? It depends on the experiment, but in the case of STO, usually TiO2 is more stable than SRO because the strontium is more volatile element. Okay, but you can make, sometimes you can make it somehow, you can, by controlling this chemical potential, you can make this external terminated surfaces more stable to than internal terminated surface. That is possible by controlling your experimental condition. All right, and making the surface means that you are changing the periodicity of your material. Okay, of course you do not have the periodicity along the normal direction, but you still have the direction, periodicity along the surface direction. For instance, in the case of the gold 100 surface, okay, you can see that this blue one corresponds to the unicell. All right, okay, so this blue one is the periodicity that result by just simply cutting the bulk structure. Okay, so so in this case usually we are naming it as 1x1 surface unicell. Okay, so before any kind of relaxation, just by cutting the bulk, you can make the basic 1x1 surface unicell. All right, and specifically, if the lattice parameter of this FGC is A, then these two surface lattice vectors from this figure, you can see that this is half of the A, 1 on O, and half of the A minus 1, 1, O. All right, so you are changing the periodicity of your material. Okay, so this 1x1 surface units correspond to the smallest cell for the unconstructed or bulk terminated surface. And in order to, but since we are always imposing the periodic boundary condition, and the surface by itself, it breaks the periodic boundary condition periodicity along the normal direction or the z direction. So we have artificially introduced periodicity along the normal direction. So that means that we are actually the modeling surface using the slab and the vacuum. So rather than just the real surface would be, there's a surface and the materials in a semi-infinite way, right? But rather than the semi-infinite material, we're just cutting it in the other direction and then make these two surfaces up and down, okay? Like that. So we call this structure as a slab. Okay, make it a slab. And by inserting this slab and the vacuum between the neighboring the slabs, we can make a periodic structure or periodic modeling of the surface. All right. So, so in this case, this lattice parameter, the lattice parameter that's including the slab thickness and the vacuum correspond to the lattice parameter along the surface normal. Is the lattice parameter along this supercell. Okay, so then how we can choose the vacuum length and also the thickness of this slab? So, ideally, extremely long vacuum and a very thick slab would correspond to the real material, right? But as I mentioned just before, we always have to somehow, cut it, make as small as possible to make the computation feasible. Okay. So the number of layers, here in this case, it should be chosen such that the physical property that we are interested in, or becomes the similar, such that the physical property in the middle layer, like lattice spacing, or in the case of the electronic properties like energy gap, or density state, those things are similar to the bulk structure. In that case, we can say that this is a slab is fairly well represent the real surface and semi-infinite bulk. Okay, right, and also the vacuum, it should be big enough to avoid any interaction between the two slabs. Okay, so that is how we can make the 3D model of the surface. And this is an example of the gold 100 and 1x1 surface. Okay, so here we have introduced 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so total 16 layer, right? The 16 layer of the gold to make the slab. Okay. And all right, and so the lattice parameter is 4.08 angstrom, right? And the lattice parameter or the surface lattice vector is 2.885 angstrom. And you can make the structure file like this, okay? And each of these atoms correspond to the atoms in here. You can see that it is periodically repeated along the lateral direction. And then again, like a defect, you have to relax it because the interlayer spacing, the spacing between the different layers, it should be affected by the vacuum region. So we have the relaxed structure, and you can see that the interlayer spacing, the spacing between these two layers, D1, 2 is the space between the first and second layer, D2, 3 is the spacing between second and third layer, etc. Okay, and so this is the spacing along the surface normal direction. So this is the spacing at the top layer, and this is the second layer, right? And you can see that this is initial. So initially, since we have the bulk terminated, every layer has the same, interlayer has the same spacing, right? So 2.04, which is the bulk. And then after relaxation, you can see that the first and second layer is actually get closer, right? And it results in the smaller interlayer spacing. And then the second layer, or the layer space between the D2, 3, that becomes slightly longer, all right? So actually this is consistent with the experiment. Experimentally, from the ES spectrum, you can detect this interlayer spacing with high precision. And in the case of the gold, they found this is 1.96. You can see that it is quite good agreement with here, okay? And also the second layer is slightly expanded, and this is also well reproduced here, okay? So then why this first and second layer get closer? Because the metallic bonding usually favors the larger electronic density, okay? So metallic bonding, so this is metal, and so as it is schematically, this is surface atom, and this is the subsurface atom, and etc. And since there's no vacuum, there's no atom, so this is a vacuum. So this surface atom has a smaller electronic density. In order to compensate it, it gets closer to the second atoms, right? That subsurface atoms. By doing so, it can increase the electron density at the surface site. Okay, so that is why this interlayer spacing between first and second layer is reduced compared to the crystalline state. But this is only the case for the metallic surface, right? In the other surface, like the silicon, is quite different. Okay. And one thing that we can compute from this calculation is the surface energy. The surface energy, in order to calculate it, we first calculate this atoms, the energy of the surface model or slab model, which is like that, and it compares with the bulk atoms, bulk energy. So the difference between them is, so this is the higher energy because you have made a surface, so it is energetically it is higher than the crystalline state. Take the difference and multiply with the number of atoms. It gives the energy difference between your slab model and the bulk model with the same number of the atoms and in the surface slab, right? So that the difference is simply the surface energy to make this slab structure. And in a slab structure, we have two surfaces, right? So therefore, you have to divide this 0.95 by 2, and it will give you the 0.47 electron volt per each surface, right? Top surface or bottom surface. Okay, so then since the surface energy is usually defined as the energy per area, we have to divide this energy with the area of your surface, right? In this case, using the lattice parameter, you can calculate it, okay? And so, and you can, in terms of the MKS unit, 0.92 joule per meter square. And it compares, in comparison, in the case of the gold 111, so that was the gold 100. In the case of the gold 111, it is 1.500 per meter square. So it is approximately the same order, right? Okay, so surface energy, usually the classical potential is not good at in giving in surface energy. So in order to get this more accurate value, we actually have to use the quantum modeling. But anyway, but it gives you the similar magnitude. Okay, so that's how we calculated the surface energy. And one application of knowing the surface energy is to predict the shape of the nanoparticle. This is known as the Wolf construction. So the equilibrium shape of the crystal is anisotropic. Okay, so it tried to minimize the total free energy, and the free energy consists of the bulk energy and the surface energy. All right, and long time ago, by minimizing this surface energy with a fixed volume V, the Wolf has found that the condition of the minimum surface energy condition such that the surface energy of a certain direction divided by the distance from the center to the surface, or the distance from the center to the surface is always constant. Okay, all right. So by following this condition, you can predict. For instance, this is an example of the platinum nanoparticle, and this 111 has the lowest surface energy, and maybe the 100 is the next, or maybe the 110 is the next, and followed by 001. And using this Wolf construction, you can predict this kind of the shape of the nanoparticle. All right, so that's one application of using this surface energy. So in the practice session, you will learn about the computing the surface energy of the 3 different directions of the gold surface. All right, and then the final topic about this surface is the surface reconstruction. Actually, the surface, the bulk terminated, we only focused on this bulk terminated structure. But in some cases, or actually in many cases, since the surface has a very unstable bonding, so it will induce some form of the reconstruction or reforming the bonding. The most well-known example is the silicon 100 surface. And here, this is a bulk terminated surface. All right, the silicon has usually the full bonding. All right, so it has 4 tetrahedral bonding, like okay, up here, okay. All right, like this is a 4 silicon bonding, okay? And in 100 surface, you have cut these 2 bonding, okay? It's a dangling bond, all right? So, can you please come over here? It's a little embarrassing, but all right. Okay, the same pose like me. Okay, okay, here, right? So 2 atoms are as a dangling bond. But what they're doing is actually forming, okay. Here are my hands. Okay, like that. Okay, this is more stable, a little bit more stressed. Okay, so this is so this is what happens. Thank you for your cooperation. Okay, so this is what happens here. Right, these 2 atoms form a 2 bonding or double bonding, and they make this as a new configuration. So this is energetically much more stable than the bulk terminated 100 surface. Okay. So this is called the reconstruction, the surface reconstruction, right? The bonding, unstable bonding is somehow stabilized by restructuring the configuration. And so one consequence of this reconstruction is that it changes periodicity. Like originally it was 1 by 1, but in order to form the bond, the periodicity is broken, and periodicity is changed to 1 by 1 to 2 by 1. Okay, so but it expanded because these two atoms are now is getting closer, and this is farther and closer and farther and closer, like that. Okay, so following this periodicity, we call this as a 2 by 1 surface reconstruction. All right. And actually, this is what we can observe from the STM, scanning tunneling microscope image. You can see very small dimer structures like, along this certain direction. And this is exactly represent this 2 by 1 surface reconstruction of the silicon surface. Okay. Okay. Right. Okay. So, and actually, this is not limited to 100 surface, but for any other kind of the surface, usually they have some certain sort of the reconstructed structure. Like for instance, in this silicon 111 surface, there is one Wegelin bond that is pointing toward the z direction, and in this case, the reconstruction pattern is very complicated, very well known. The 7 by 7 reconstruction, which is also called the Takayanagi reconstruction surface. Maybe he was the professor at the University of Tokyo. The very famous patterns, revealed by some of maybe Ilse spectrum or something like that. And so, and people later found that actually this is STM image, and it reflects this underlying atomic structure like that. Okay, so it's quite complicated. There are some the dimers and add atoms and some of the cavity, right? So people later compared this modeling and STM image, and they've concluded that actually this construction looks like that. So it's a highly non-trivial reconstruction pattern. In the case of the silicon 110, we have certain reconstruction like that. So in this case, it does not really make a new bonding, but this silicon atom at the top is somehow changes. It looks more like an sp2 bonding, or rather than sp3 bonding, and so it changes its the symmetry that was given by this original Berke-terminated structure. Okay, so and this is the 1 by 1 reconstruction surface, and sometimes or it is more, this 2 by 1 reconstruction is more stable than this 1 by 1 repetition. Okay, so you can study various kind of reconstruction. What that I want to make a comment is that this reconstruction is actually depending on the environment. For instance, if your silicon surface is exposed to enough amount of the hydrogen gas, then rather than forming the reconstructed surface, is more favorable to by simply attaching one of the hydrogen, atomic hydrogen, to the dangling bond. Okay, because the silicon hydrogen bond is really similar to the silicon-silicon bonding. Okay, so by placing, so the reconstruction patterns that we discussed so far is largely applied to the vacuum environment. But when there are ambient gas atoms, then your reconstruction patterns can quite different. All right, so it should be kept in mind. All right, and during the first session, you will learn about this, how to define this stabilized reconstructed surfaces. Okay, all right. So that's the end of this theory session. Any question?
So today we're gonna learn how to calculate the defect formation energies and the surface energy from lamps. So first example is to calculate the vacancy formation energy of copper metal. So the input file is the bulk1.in in the practice material. So we're gonna use EAM potential, so the unit is gonna be metal, and this you already learned the basics of lamps the last lecture, right? So all of the data file and the potential file is included in the practice materials, so it's going to load that files. And the change box command sets the scale of the simulation box, and since we are going to calculate the defect formation energy, we're going to make the supercell with replicate 333 command here, and we're going to minimize the potential energy with minimize command. So this bulk1.in calculates the energy of bulk kappa. So if you learn this, if you run this bulk.1in, it's going to calculate this. And when you look at this log file, here there's going to be this relaxed energy of bulk kappa. So you can copy this energy and put it in some Excel file or whatever you want to calculate this formation energy. And next it's gonna be the copper cell with one vacancy. So we're gonna delete one atom from the bulk cell. So before that, we have to group one of the copper atom. So this group command will group one of the copper atom. Here we make the first copper atom as the group name of my atom, and then this delete atom command will delete this group of my atom. So this delete command is gonna delete the first copper atom and make a vacancy. So we're gonna run this. Vacancy.in. So when you look at this log file, it's gonna go 61 steps to relax this vacancy cell. Copy this energy and put it in Excel, and there's gonna be this vacancy formation energy. This equation is from this slide, so you can copy the LAMS result and calculate the vacancy energy, vacancy formation energy. And with this vacancy formation energy, as you learned from this previous lecture, you can calculate this vacancy concentration. So if you want to see the movie of the vacancy cell relaxation, then you can put this movie file to VMD here. There is vacancy here. So if you zoom in, there's vacancy here, and as the relaxation runs, you can see that it relaxes really little bit. Can you see the relaxation? It just slightly moves here. So anyway, This is the relaxation pattern, and this is how to calculate the vacancy formation energy. So anybody have a question? Can anybody run this procedure like this? Okay, next is the substitutional defect in copper. So it's going to be a aluminum substitutional defect. So you can read the copper aluminum data in the practice material, and the potential is going to be EAM potential for aluminum copper system. And as previous example, we're going to make a 3 by 3 by 3 supercell, and then here we change the dump to dump modify command to see the to make it dump the coordination as the absolute coordination, so we can calculate the distance of copper and aluminum, and this set command changes the one of the type 1 atom into type 2. That means that one of the copper atom is going to be aluminum atom. And then relax this. So when we see this movie file, you can see the absolute atomic coordinations of these atoms. So what we are trying to do is do the supercell test to see how large the supercell is needed to see the distance of copper and aluminum atoms distance converged. So the last line, after all the relaxation is done, there's going to be this line. So the first atom is aluminum and the second atom is copper. So if we calculate the distance, it's going to be 2.59, like here. And when we change the supercell size here, like in this case we did the 3 by 3 by 3 supercell, but if it changes to 111 or 222 or something like that and calculate the same distance, it's going to be plotted like this. So in this case, the largest supercell, which is 4 by 4 by 4, is the reference. And we can see that 3 by 3 by 3 or maybe 222 is enough for the distance convergence. 너무 빨라? Is it too fast? Okay. I'll slow down a little bit. So, anybody understand this? If you have a question, then raise your hand and he's gonna come and help you. So if you look at the movie, this is the aluminum atom and the other is copper atom. And you can see the slight movement of the neighboring copper atom. Can you see this? So So this is metal, so the relaxation is really softer. Okay, so the next example is silicon self-interstitial. And as you learned from the previous lecture, there are 3 kinds of silicon self-interstitials. And the relative interstitial energy is really similar, these 3 kind of interstitials. So it is always an issue which one is most stable one. So we're going to calculate the interstitial formation energy with tensor potential. So there is a silicon.data file in the practice material. It's a perfect bulk structure of silicon diamond. So there's going to be 8 atoms in the conventional cell. And the first one is to calculate the structure energy of 1-1-1 split silicon interstitial. So the first lines are similar to the previous ones. We're going to make 3x3x3 supercell. And we're going to create 1 more atoms in the 1-1-1 split position. So first we have to group one of the atoms which has ID of 6 and create the atom just next to this atom 6, which is 0.05 angstrom to the x-axis and minus 0.05 angstrom to the y-axis. And we're going to displace the original atom to the opposite way of the created atom. So it's going to be like this structure. So So if you run 110 split .in, there's gonna be so this is the relaxed potential energy, and you copy and paste here. And if you look at the relaxation pattern, it's going to be a little bit more interesting than the metal examples before. So starting point is like this. As we displace the atom just a little bit by 0.05 angstrom, the distance between 2 atoms is really close like this. But as the relaxation goes on, it splits and become relaxed structure. So that we calculated the potential energy of split interstitial. And we can do the same with hexagonal and tetrahedral site interstitials. creating one atom in certain position, which is hexagonal or tetrahedral interstitial site. So you can really quickly run this simulation. Then copy the potential energy somewhere. So in order to calculate the interstitial formation energy, we have to know the perfect bulk, potential energy of perfect bulk. So you can run silicon bulk dot in to see the potential energy of perfect silicon bulk. So this is how you calculate the interstitial formation energy. And you can see that with tensor potential, hexagonal interstitial is most stable one. Everybody follow? Next one is calculating the surface energy of gold. We're gonna calculate three surface energies, which is 100 and 110 and 111. So just like the formation energy of defect, we first have to calculate the bulk energy, perfect bulk energy. And this time, instead of reading the data file as the previous examples, we're gonna make the structure within the input file. So it's gonna be these comments. These comments are to make the structure within the input file. So first we have to make the lattice. In this case, gold is gonna have FCC lattice, so the lattice type is gonna be FCC with the lattice constant of 4.08 angstrom. And this region comment is to make certain region. So we have to make, we're gonna make a region with block type, which is box of 4.08 angstrom of each length and depth and height. And the name of this region is going to be seam box. once we make this region, we can make the simulation box or create atoms within this box. So first we have to create this box. The sim box is gonna be the box where we perform the simulations. And this one command means that we're gonna create one box as the simulation box. And we're gonna create one atom to the box. And since our box has a lattice of FCC, it's gonna create atom to every lattice point. And the mass of the atom type 1, which is gold, is this value. So with these 5 commands, we created a simulation structure within this input file. The rest is same. We use the EAM potential and minimize the structure energy. So work 2. And the potential energy is, structure energy is here. So you write it down somewhere. And then we're gonna calculate the structure energy of one surface slab with 100 direction. So in this type, we're gonna use the lattice command with custom type lattice command. As the previous example, the lattice constant is 4.08, but this time we're gonna use the primitive vector components command and this basis command and orient command. This is because, as you learned from the previous lecture, the lattice vector direction is changed with this slab structure. So we have to change the x and y lattice to 110 and -110 direction. So the orient command does that, changes this direction of this lattice. And then, since we use the custom type of lattice command, we have to give it the location of the basis. So this is in order to make this FCC slab. And once we define this lattice, then we have to define this simulation box and the box where we're gonna put these atoms. So the first simulation box is gonna be like the box from here to here, where the simulation is going to be performed. And the field box is where we're going to put these atoms from here to here. So if you look at this command, the simulation box is 10 angstrom longer than this field box. So it means that the vacuum is going to be 10 angstrom. And these atoms is only going to be filled until 20.4 angstrom. So that's how you make this slab. Or if this is too complicated, you can just use you can create the structure file as the previous examples and just read this structure file. If that's what you want, either way is okay. So once you create this input file, you can calculate the structural energy here. And you can do the same with 110 surface. This time the orientation of the axis is 110 because it's going to be 110 surface. And the others is similar to the previous examples. You can do it by yourself. And same with 111 surface. This time the orientation of the axis is 111. Others are same. And with these equations, you can calculate the surface energy of gold. So here we can see that 111 surface has the lowest surface energy and 110 has the highest surface energy. Okay, so the last part is to calculate the surface energy of silicon 111 surface, and we're gonna compare the surface energy with no reconstruction and the surface with reconstruction. So as usual, you first have to calculate the perfect bulk energy. And the first is surface with no reconstructions, so it's bulk terminated. The part creating the structure is same with previous examples, but in this time it's not FCC lattice but diamond lattice, so the basis positions is gonna be these 4 points. So this is for creating the diamond lattice. And since we are doing the 100 surface, the orientation is going to be like this, 001. And like the previous example, it's going to be a slab with vacuum of 10 angstrom. So the fill box is, the z-axis of fill box is 10 angstrom smaller than the simulation box. And the mass of silicon is 28.0. So if you run this simulation, it's going to give you the structural energy of silicon slab, bulk terminated silicon slab. So, as I explained before, you can use this VMD to see which atom has which ID, but you have to be careful because the index of VMD is less than the index in the LAMS file. So the first atom in LAMS has ID of 1, but in VMD, the first atom has ID of 0, so that you have to be careful. And the surface atoms has 31 ID of 31 and 32 in this structure. So the second input file is the structure of surface reconstructed silicon slab. And this time, in the first input file, there's no, it's just simply bulk terminated slab. So even though you relax this structure, it's gonna end up in the local minimum of low surface with low reconstructions. But if you want to see the surface with these reconstructions, you have to move it in the initial position to avoid the local minimum and go to this global minimum of reconstruction. So first you have to move these atoms of 31 and 32. Moving these atoms in y direction of 0.5 angstrom and minus 0.5 angstrom, and it's gonna make these surfaces reconstructed. So if you run this simulation and check out this movie, this is the silicon surface slab, and as you run the relaxation, you can see the structure is changed and goes to more stable state here. So you can write down the stable structure energy from the log file and calculate the surface energy. So with surface reconstruction, you can see that the surface is stabilized by about 8 joule per meter square. So this is today's practice, and if you have any questions or problem with this practice, you can raise your hand and ask the TAs.